Let's go to the Whit and Grit book. We'll start there in chapter 19. Whit and Whit, chapter 19. And what we're doing here, let me get my screen the right size. Okay, that looks good. We're doing something called the chi-square test. And sometimes you see this written as, actually you see this written as the chi-square analysis, or analysis, even an analysis of variance. But I'm just going to say chi-square. Chi is the Greek letter that looks like, kind of like that. Sort of a big fancy curly Q X, and an exponent of 2 means squared. So chi-square. Little background on chi. How many of you don't have to weigh in, but how many of you just think to yourself, get bent out of shape when you see that? Xmas. They're taking Christ out of Christmas. Well, actually, no, they're not. I mean, they might be, but that's not the. Chi is the Greek letter that is the first letter in the word Christ. That was a shortcut, sort of a coded way, but it meant Christmas. It doesn't mean Xmas. Nobody's trying to, well, I can't say nobody's trying to X Jesus out. I don't know that, but in general, that's not why you say it that way. That's not where that came from. It's the Greek letter chi, the same Greek letter we're talking about here. So there's nothing evil about the letter chi. You may think so in terms of statistics, but that's another story. But chi-square. And chi-square is interesting in a number of ways. Chi-square, first of all, is a non-parametric test. You're all saying, okay, I believe you. What parametric statistics are? Remember that lesson where we had the sample of all the samples? We said everything turned out into a normal curve if you do all that, no matter what you start with. Okay, and so we have used that model to be able to use what we understand about the normal curve for these previous analyses, even though our initial data was not necessarily normally distributed. It was parametric because we could use that. We talked about the rule of large numbers and things like that. Chi-square is non-parametric. Chi-square is not based on a normal curve. That's the difference between parametric and non-parametric procedures. Chi-square is the only non-parametric thing we're going to do in this course. The other thing one other thing chi-square does, it kind of brings us back full circle to one of the things we talked about in the very, very, very first lesson, and that had to do with levels or types of data. Remember the lowest type of data? That's not a rhetorical question. It's nominal. Nominal data is the lowest. Now, we've used nominal data as grouping data, but we've only used that to kind of sort through higher level data. You know, we sort test grades into this group and that group. Well, which group it is nominal data, but we analyze the more continuous data with all these other procedures we've had. Chi-square can be used if you have only nominal data or categorical data, where all you can do is count and sort and categorize. So it kind of brings us full circle back to the lowest level of data we have. Now we'll talk about two kinds of chi-square. Going to talk about a one-variable test and a two-variable test. Sometimes you call these one-way or two-way chi-square. Two-way chi-square, which again we'll get to, we'll use the phrase contingency table sometimes, but we'll sneak preview of coming attractions shortly. What chi-square does, it compares what you observe with what you expected to observe. Do you get more or less than you expect? And I'll give you a real clear example of that in just a minute. Let me say it again first. Chi-square compares what you observe with what you expected to observe. So we talk about two different kinds of values. We talk about observed values and expected values. And the really good example I was talking about is on page That is top page 426. And it's an example involving blood type. Excuse me. So let's say we've got blood type. Okay. And we've got data from 100 people. And our blood type is either going to be O, A, B, or AB. And we observe that we've got 100 people, we find 38 of those are type O. We're not going to worry about the positive and negative. 38% type O. 38 of them are type A. 20 are type B. 4 are type AB. Now, these are observed values. What would I use for expected values? Well, no, there needs to be some kind of logical system behind it. Let's say that we know that on average how many people or what percent of the people have what type blood. So we know, for example, that 44% have type O blood. So out of 100 people, we would expect 44 to have type O. So my expected values, and I'm generally just kind of as a convention, right? I'm writing expected values in parentheses just so we know we separate them off like that. So we expected, out of 100 people, we expected 44. We got 38. Well, is it a big deal that you got 38 instead of 44? Is that a significant difference between what you got and what you expected to get? And I don't know. It goes back to my old example. If you flip a coin 100 times, you expect 50 heads. Actually, this is a better example for chi-squared than I've used in some other contexts. You expect 50 heads. If you get 49 heads, is that a significant difference? Probably not. If you get 48 heads, probably not significant. If you get 40, I don't know. If you get 10, yeah, that's probably a significant difference in the 50 you expected. Here, we expected 44, we got 38. I don't know if that's a big difference or not. We also know that 41% of the people are type A, so out of 100 people, we would expect 41. We got 38. Those numbers are even closer than the first set would be. 38 and 41 are closer than 38 and 44. So I still don't know if that's a big difference or not, or if there's a big difference anywhere. For type B, 10% of the people are type B, so we would have expected 10. We got 20, so we got a little more there. And 5% of the people are type AB, so we would expect 5. We got 4. I don't know if this is on target or not. Likewise, let's say you've got 100 marbles in the bag and 75 of them are red. If you draw at 75 marbles, you're probably not going to get exactly 75 marbles. But you're probably going to get pretty close to that. I said that's what's in the bag. Yeah, I said we know that, yes. Let's say let me change my. Let's say if we take out 3 marbles. I'm sorry, we take out 4 marbles. We would have expected 3 reds. We might not get 3 reds. If you got 1 more or 1 less, it's probably not a big deal. The number's too small to mean much anyway. Here's the chi-square, and we're gonna, for the one variable chi-square, we're gonna calculate this by hand. If you look at, I think it's lesson 40 in your Green and Salkin book, it's more trouble to make SPSS do this than it is to calculate it by hand. Now, that's not going to be true for the 2 variable chi-square. But for the 1 variable chi-square, it's going to look like this. Here's our formula. Our chi-square formula, the chi-square value is equal to the sum, and this is the sum for each piece here, of the observed value minus the expected value, that means frequency observed and frequency expected, whatever that is squared because it's a chi-square, divided by the expected value. So we're going to do observed minus expected, square it, divided by expected. Do that for each, in this case, 4 times, and add them all together. So for the first part, for the O-type blood, I'm going to say 38 minus 44, whatever that squared is, divided by 44. Now look what happens here with each of these. 38 minus 44, in this case, is a negative 6. That tells you, and we've done this thing, this goes all the way back to our z value. You take what you've got, subtract what you expected, or you take your number, subtract the overall mean. It tells you how far away you are from something. In this case, we get a negative 6, so we have 6 less than we would expect. But look what happens when we square it. I don't care if it's a negative or positive number. When we square it, we're going to get a positive number. And then you're going to divide by a positive, so you're always going to get positive numbers here. The next cell is 38 minus 41, whatever that is squared, divided by 41. The next is 20 minus 10, whatever that is squared, divided by 10. And the next one is 4 minus 5, whatever that is squared, divided by 5. And I think I've left myself enough room on the last slide. So, and I didn't have my calculator, obviously. Let's go here. So get your slide rules out and confirm this for me, or with me. 38 minus 44 is negative 6. Negative 6 squared is 36, so whatever 36... I'm going to write this way. 36 divided by 44 is. 38 minus 41 is negative 3. Negative 3 squared is 9, so 9 over 41. 20 minus 10 is 10. 10 squared is 100. 100 divided by 10 is 10. 4 minus 5 is negative 1. Negative 1 squared is 1. 1 divided by 5 is 0.2. So my chi-square value is going to be whatever 36 divided by 44 is, plus whatever 9 divided by 41 is, plus 10 plus 0.2, and I get a chi-square value of 11.237, more or less. Anybody amen that or not? Okay, good. I see the number, and I see a couple of yeses. Okay, so there's my chi-square number. Now, if you go to the back, again, our magic tables again. Our chi-square table is on page 537. That is table B of that appendix. Now look what else we have to know in terms of which row to look at. It's the same piece of information we needed all along for the tables. Page 537, table D. And I'm going to look at, I guess, does it have us do the 0.05 level? Yep, 0.05. Okay. So, again, because when you use the table, that's the only time you need to worry about a critical value. When you're using SPSS, you don't have to know about the critical value. You just look at the p-value. All I know is for my critical value here, the degrees of freedom is, if you look on page, for a one-sample chi-square, Page 428, degrees of freedom is the column of number of columns minus 1. I had 4 columns. We had 4 different blood types. So that's 3 degrees of freedom. So for 3 degrees of freedom at the 0.05 level, I'm looking at a critical value of 7.81. The question is, how does my 11.237 compare with 7.81? It exceeds it. So again, if our calculated statistical value is greater than the critical value, then yes, there is a significant difference. And the answer in this case is, yeah, we got significantly different than we expected. If the chi-square value is greater than the critical value, just like if the t value is greater than the critical value, or if the f value is greater than the critical value. So what we know from this, the question was what numbers we're comparing. So what we know from this is all we know is that p is less than 0.05. That's all we know. The advantage of SPSS, it tells you what the p-value is much more specifically. So you know that it's less than 0.05 or not. But in this case, for a one-sample chi-square, it's just, believe it or not, it's easier to do it this way. If you look at the examples, the data set for less than 40 in Green and Salkin, you're going to find a different row for every case. So you'd have like 100 rows here. I'm just not going to do it that way. Another reason is because this isn't as useful as the two-sample chi-squared is. But you got a couple of things here. You've got the chi-square formula, which is this, is always the same. That's always the chi-square formula. The question was, would it be correct that type B was where the difference was? Not necessarily. I'm skipping a part here because we're doing it manually. The follow-up question, like the analysis of variance, okay, if you've got significant difference, where is it somewhere? All I'm trying to determine right now is just a do you know what time question. Yeah, there's a significant difference somewhere. It would require post hoc follow-up analysis to determine if maybe all these things were significantly different than what you expected. We don't know that. I'm not going to tackle that just yet. So I just go through this one sample chi-square just kind of as an example to show you generally how it works. The meat of it is really in the two sample chi-square. Are there questions about this value at this point? Okay, so let me stop there for now.